9:30. David saying, I've just woken up. I have a tute now. Can you please go tutor 1A?
What's this?
David slept in.
Which David?
David.
Yeah, of course. And
Big
so,
day.
big day. So he called Matt Ryan saying, can you please tutor 1A for me? I've just woken up. And this was 3 after the tutor's meant to start. So Matt's just like running out, just swearing at me. Doesn't know the fucking course. And he's rushing out to go to the
Wow.
trying to get the tutor room. It was just
Could have been bad if he wasn't at uni.
yeah. It was like someone would die.
That reminds me of my friend was doing so at abattoirs. You have to have a vet to do like a health check, and he overslept because they start really, really early. So he phoned them up and said, "I overslept. I'm really, really sorry." Put a couple through. I'll check them. They went, "We start 5 o'clock. If they go through and they're not healthy, you should have been here." they just went, "Nah, you're not here. We don't stop the abattoir." Very disconcerting.
I mean, yeah.
They can't though. All that stuff runs on way too tight a schedule, especially if they're sending the stuff out.
Yeah.
Like you
Yeah,
just can't
no,
afford to.
no.
If no one went to his prac, there would have been 30 students sitting there going, huh?
We did abattoir work, and it's really scary because you went to this place out in the middle of nowhere to the abattoir, and every so often you have to stop the machines because there's a carcass coming through you want to check, and it's really scary because you stop the machines and you start hearing this, and what it is, it's their carving knives. They're hitting them against the sheath because they get paid on each carcass. So as soon as they finish, they go drinking. So you have a lot of very angry Scottish people with knives, and it's really scary because you stop it and slowly hear this, and it just gets louder and louder and louder. You're like, yeah, that looks fine, quick. Very, very disconcerting. But the best bacon is ever in the cafe. So, ups and downs. Okay, so, lecturing, like everyone's like, lecturing's really hard. No, I've never been killed, threatened, punched, bitten, shat on. I've been shat on actually, but that was a bad lecture. But
I just fucking need a hug from mum now after hearing that story.
I think we have an emergency button that mums will arrive.
Order in 10 months.
Cool. Okay, so we're continuing this idea. To some extent, a lot of the stuff we've been doing at the moment has been about feature selection. You know, the general framework has been, how can we reduce the number of predictors down? So we've done things like, subsampling, forward selection, backward selection. We then started looking at almost automatic processes like ridge and lasso, which put constraints on the coefficients. So here's my summary of what I just said. So we've looked at subset predictors, we've shrunk, etc. Now what we're going to do is we're going to transform the predictors. So we're going to introduce 2 methods today. They're going to do dimension reduction. We're going to do PCR, which is principal component regression, and then partial least squares. Okay. So just as an indication of where we're going today. So here's the setup we're going to do, is we're going to say, we're going to create ourselves some new predictors. And the idea is we're going to take our P original predictors and we're going to reduce it down to M predictors, where M is less than P. And I'm going to use my new predictors, I'm going to call them Z1 up to Zn. So how are we going to create this new set of predictors? Well, what we're going to do is we're going to consider a linear combination of the original P predictors. So for example, Zm in this case, so the nth Z, will be J equals 1 to P, some phi Jm times xi. So I take each of my original predictors, I'm going to multiply it by some sort of constant, add them all up, and that's going to be my first new feature. Then I go back to them and I get a whole new ones. So I'm taking a new set of predictors that I've created by a linear combination of my original predictors. Then all I do is I go to my model and I just fit a linear regression where the predictors now are my new z's as opposed to the original x's. Cool. So let's just have a quick think about that. Just a little bit of maths here. If you think about what we're doing in the original, if you go back to that second equation, you've got the summation as m goes from 1 to m, theta m, zi m. Well, if I rewrite that, what is the zim? That is a linear combination of my x's. So I can say, I've just substituted where I had the zim. I said, well, each zim is just j equals 1 to p, phi j m x I j. It's just a linear combination, so I substituted in. These are all nice and finite. I don't have to worry. I can just now interchange my summations. The theta m doesn't have a j in it, so it can go on the inside. So I can rewrite this as j goes from 1 to p, m goes from 1 to m, theta m, phi j m x I j, which is a complicated way of writing it down as what we expected before. When we look at our mean model, it's usually going to be some linear combination of the predictors. As our linear regression model is that we believe the expected value of our yi's is some linear combination of the predictors plus some noise. So I've got this beta j. The beta j is complicated. The beta j is the summation as m goes from 1 to m, theta m, phi j m. So what does this mean? It just means in this process, we are taking our standard linear regression and we are adding constraints on the coefficients. So as always, whenever we start to reduce the flexibility, we know that bias tends to go up and variability tends to go down. That's one of the key stories we've had all along with that bias-variance trade-off. Anytime I have a more flexible model, bias goes down, variance goes up. In this case, I've done the opposite thing. It's got less freedom because we're constraining them. So what do we do in these dimension reduction protocols? It's a two-step process. First of all, I take my predictors, I transform them, and then once I've got them transformed, I just go and fit a linear model at this point. You can actually fit more complicated models, but we'll assume you're just going to fit a nice linear model. So let's start with the first one, principal components regression, or PCR. So what I'm going to do now is I'm going to do a very fast introduction to PCA. I'm not going to go into detail because I'm going to do a whole lecture on it when we get to unsupervised learning later in this course. So at this point, it's like suspend your disbelief. Believe me, there's a thing called principal component analysis. And then later on, we'll come back and we'll do it in detail. So let me sort of illustrate the key idea. So here I've got some data where they looked at the population size and the amount of spending on advertisements. And each of these dots is an individual observation. And if you look about it, you can sort of say, well, look at that data and think about which has the most variability. So if you look at the green line that goes from bottom left to top right, that represents what we call our first principal component. The first principal component is the direction within this data has the most variability. And later on I'll show how you actually calculate that. But the idea of your first principal component is you look at your data and go, is there a direction which has the most variability within that data? The blue dashed line is my second principal component. You say, once I've taken into account that first principle, which direction that's uncorrelated with the first direction has the most variability? So you're sort of taking your data, and first of all you're going, if I sort of squint my head in a certain direction, do I get most of the variability? Once I've taken into account, what about the next lot of variability? And generally what PCA is doing is, and we'll get to it in detail further, the problem is in 2 dimensions it's easy. Once you get to n dimensions, it's really hard to see the sort of sense of the data, how it clusters. So what you're doing with principal component is you're basically rotating and shrinking and pushing your data around, so eventually you can see where most of the signal is. In this case, by most of the signal, where most of the variability is.
Are they always going to be orthogonal?
Yes, because they're uncorrelated, hence orthogonal. So you'll see when we do it later, first of all, you solve an equation where you say, find me the direction with which has the most variability. Now, find the direction that has the most variability that is basically orthogonal to the first direction. Then the third one, find me the direction that is most variability that is orthogonal to the first two. And you should start to be going, is that Graham Schmidt? And as always, if at any point someone mentions a matrix, you know that eigenvalues, eigenvectors will eventually be useful. Again, we don't tell you that in first year because we'd hate you to think that anything you're doing was useful. But the one thing they taught you in first year was eigenvalues, eigenvectors. And it was the one thing that actually was really, really useful for almost everything.
Sorry, just remedial stats for people that never did stats. Why isn't the blue line the one with the most variability? Because the dots are nowhere near the blue line.
No, that's the direction. So what I'm saying, if you look at along this line, if I projected all the points down to that line,
Yep.
and then looked at how much along this line, that would have the most variability. So it's not the distance from the line,
Right.
it's the distance along the line
Yep.
that we're thinking about the variability.
Okay.
Make sense?
Yep.
Good.
Perfect.
So what we're actually doing for the first principle is I'm going to say, let's consider all linear combinations of them two variables, which was population and advertisement. I'm going to put an extra constraint. I'm going to say that all my coefficients are going to be bound. Because if you think about it, if I wanted to maximize my variability, well, I just make them coefficients bigger and bigger and bigger and bigger. So you have to have a constraint. So my constraint here is that the sum of the squares of them is equal to 1. What I'm trying to do is I'm trying to say, if I take my population, now I've basically centered my population, so I've taken off the mean of the population and the mean of the ad. If I took this linear combination, so I take my phi11 times my population, centered, plus my phi21 times my advertisement, and I calculated that variability, the optimization problem is just go and find the values of theta11 and theta21 that maximizes that variability. And as I said, because it would be very easy to go, right, I'll set theta11 to infinity, and that's really maximized that variance. We're going to constrain it. If you solve that problem, you would find that basically if you took the phi11 to be 0.839 and the phi21 to be 0.544, that would maximize your variance. And later in the course, we'll do the calculation, show exactly why that turns out that way. So we're going to give these some names. So these two coefficients, 0.839 and 0.544, are called the principal component loadings. So that's it. That's your first principal component. So that's your linear transformation of your predictors, in this case the two predictors, that basically gives you that nice blue line. It gives you the direction of that blue line, and that explains most of the variability. This sort of comes back to the question that Ben had. If you take my data points and now project them down onto that line, so I'm calculating the amount each of these points is along that line, that's what we're going to call the score, that has the most variability. That's the first principal component. And in fact, for each observation, now I can actually calculate the ZI1. And I'm going to call them the principal component scores. So now with my data, instead of having the X1, which is the advertisement, and the X2, which was the advertisement. So I said, no, I said, yeah, I got the wrong way. Instead of having pop and advert, now I have this first principal component, this new number for each one, which I've calculated, which is I've taken that observation, I've projected it down onto that line and said, how far along that line are you? So, now we've got that, we can get the second principal component, and that's going to be the linear combination of the variables that's uncorrelated with Z1 and maximize the variance. Now I have an extra constraint. It has to be uncorrelated, so it has to be orthogonal, and I'll get my thing. Now, this data is two-dimensional, so this data only has two principal components. If ever I have P predictors, and I'm going to assume my P predictors are linear independent, then I can have P principal components. But you say, well, so fucking what? Like, you've changed it around, you've made it really complicated. The nice thing is, if I had P predictors, sometimes I don't have to use all P. You can actually sort of do a calculation where you can go, how much of the variability in my data is explained by the first one? How much is explained by the first and the second? How much is explained by the third, second, third? If I can get to like 4 predictors, and I'm explaining 90% of my variability in the data, the rest is just a little bit of tinkering. I can reduce my space down, okay? Although, if you think about it, now when I do my linear regression, it's really complicated because you'll come along and say, well, the coefficient of on the first principal component is 0.5. So if I increase the first principal component by 1 unit, then it increases my response by 0.5. Well, that's great, but I want to know what happens when I increase advertisement by 1. Everything's now been shoved together. The other nice thing about principal component is remember that by their construction, they are orthogonal and hence uncorrelated. So if I have a lot of problem with data that is quite highly correlated, for example, this data here is quite highly correlated, the principles will be uncorrelated. All the problems I normally have with collinearity will not be a problem in my fitting of my model once I look at the principal components. And in fact, if you think about the extreme case, imagine these points all lay on a straight line. There wouldn't be a second principal component. There's no extra information contained within that.
That's a weird question.
Absolutely.
You talk
Is this
about-
back to the abattoir thing?
No, it isn't, sadly. You talk about interpretability because when you get your principal component, it's going to have a bunch of factors.
Yes.
Right? Some potentially quite small, like not non-zero, but pretty small.
Yeah.
Have you ever used a principal component where, just like before with ridge regression, you bully it into minimizing the number of factors it actually uses, so that you have a more explainable principal component?
Absolutely. I mean, you get that indirectly. You'll see in a second that you get the variance explained. But the other thing you can absolutely do is, I said we're going to fit a linear model. No. What we've done is, to some extent, this is sometimes called feature transformation. So you can do this as your first step process. I get my principal components. Now my principal components can fit in all the various models we've seen up to this point. So you can see it rather than this whole process of here's PCR, you can go, here's my feature transformation process. Once I've got my feature transformation, I'm now going to shove that into lasso or ridge or support vector machines or these various things. Now sometimes you're double dipping, there's not much point, but absolutely there's nothing wrong with you going, now I'm going to do a principal component regression with lasso. Absolutely, good question. So, how do we do it in this case? You're going to construct the first m principal components, and then you use them as predictors in linear regression. But as was nicely pointed out, beautiful non-sequitur that ended up being a sequitur, is that you don't have to do linear regression. You could use other modeling techniques. As always, the thing is you do these really fancy things, and you go back to your collaborators, and they always ask the question, that's fantastic, it predicts, it's really good, but what does it mean? And you have to do that discussion where you go, I have lost my interpretability once I've got the principal components. Although you see in a second, you don't actually. So it's quite cool. The recommendation is to standardize your peak predictors, because if you have one predictor that has huge variability, because for example you decide to measure it in millimeters where everything else was in, for example, meters, that automatically drags that first principal component towards it. So in this case, standardize, you take each predictor, you divide it by the sample standard deviation. So let's do it. And because I'm so enjoying learning all about baseball, let's go back to baseball. Because I'm just an absolute expert. I mean, to be honest, we could have chosen any sport and I'd have no idea.
Soccer?
I'm probably better with soccer, a little bit better. But I'm still, and only because as a kid I played 3 and in and I know the actual rules of the game. But I still wouldn't know all the technical details.
You know what a goal means, whereas you may not know what a CRBI is.
We talked about the CRBI, cumulative red bed indicator.
Yes.
So don't you come here with your, you don't know what you're talking
Or
about.
career runners batted in, but that's different.
Is that it? Is
Yeah.
that seriously what it is?
Yeah, so runners batted in is when I'm hitting the ball, if I hit the ball and someone gets a run in, that's a runners batted.
Wow.
Runners batted in, and career is...
Did you look at the help file or did you know this before?
No, last lecture he was just flexing on us, just like, yeah, that's that. Yeah, that's that.
I've never watched a game of baseball in my life, I just don't know.
Yeah, okay. So let's have a look at this data set I don't care about.
It's important to know these things. You never know what will come up.
Okay.
Yeah. I like the fact you think that's flexing your muscles.
Yeah.
That's what
Okay, me, you, car part now. Let's get up there and talk about baseball statistics. I will fucking. Oh, you're gonna punch me instead. I see. I completely misunderstood what this was about. Just going down the gym and just going, right, tell me another acronym. I will identify that one for you. Ooh, he's going for it's a 5-letter acronym. Ooh.
He's gone for lasso.
Oh no! So how do you do it? The package is the PLS package, and within it has the PCR function. So again, nicely, it fits within the standard formula model. So I'm going to do a PCR. I'm going to do salary tilde dot. So I'm going to do salary on every other predictor. Data's hitters. Scale equals true means that we've standardized. So it's divided by the sample standard deviation. Validation equals CV. You can put in a validation method who actually go and validate it for you. You can have leave one out, cross-validation. And then we do the summary. So let's have a look at what we've got here. Has the data, has the X and the Y, tells you the method used to fit, single value decomposition, principal components. It's considered the first 19. I'm trying to remember if there's more than that. There might be, how many have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. More. There is more, but you have to take into account that when you have categorical variables, there's going to be more predictors. If a categorical variable has k levels, there will be k minus 1 predictors in the standard representation of data, categorical data in R. What it does is it takes the first principle, you've got your intercept, and then it's got your cross-validation error, but also it's got your training, which is interesting. It's got percentage explained. So as you can see, if you look at the training part, as you increase the number of components, the proportion of variability explained increases. So you could use that as a cutoff. So you might say, look, I only care if I explain about 80%. So you start with 4 components. But often the way you'd actually choose it, the way I chose it this day, is with the validation. I went along and I found the one that had the smallest CV. And it just so happened to have the smallest. Actually, I think I chose the wrong one. I think I chose 5 in the end. No, I chose 6. I did choose 6. I chose 5, and then this morning I was looking and I went, no, I should have chosen 6. But you can use that to choose the number of components. I think the best quote I ever heard about PCR was from Gary. And he goes, I never believe it should actually work, but it always works really well. And in a second, we'll explain why it shouldn't work.
So is this saying that there were some components that were linearly dependent, or is it, because it says considered 19, so I'm not sure if it's dropped some.
No, it's just going, so you could get it to do every single component it's got. Absolutely. So if there were linearly dependent predictors, you won't have the full, so I'm assuming that if there's P predictors, you should have up to P principal components.
Right.
But if any of them were linearly dependent, you would have less than that.
And did it work that out, or did it stop when it got to 100%?
No, I think it's a default one with the 19, if I can find out for you. Tobin.
Maybe this is a dumb question. The cross-validation, what is it actually validating? Like, what's that number indicate? Like how is it measuring goodness of fit with the cross-validation?
It would take your model, it would predict, and it would look at the mean square error between your prediction in squared terms. So it's doing your standard cross-validation. Take out, fit with the rest of the data with that many principal components, then use that to predict the data you took outside. Calculating this, because it's a regression model, you will look at the sum of the squared differences. Then you put it all together. Remember how you put it all together, take into account the unequal size, and you get the mean square error.
So it's returning the PCR model, not the principal components? Am I correct?
Yes, all that cross-validation is the cross-validation for PCR.
Oh, right.
Yeah.
R, not A.
So then presumably you decide I want 6, then you just pull the 6 out of the model that you want.
Yeah. So I looked at this, I'd said do cross-validation, it's gone and done all of them, up to 19. I'll just check why it chose 19, just to answer your question, I'll find that out for you.
It says the data X has 19 predictors.
Yeah, so I think it's just said, I'll
Probably
consider
doesn't
every single
all of them.
predictor.
Yeah, it's just a lot.
Yeah, it just looked like more than 19 on the thing. That's what's freaking me out.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
But salary is taken out of it.
So it's taken out, so 19.
Okay, so it is 19.
Good.
It was a counting error.
Yeah, that's advanced stuff. That
We
is
don't do
for me.
arithmetic, we do maths.
right.
Yeah, exactly. Which is arithmetic with errors.
With computers?
So, also built in is a really nice thing, a validation plot. So here I've got MECEP is the validation type. You can choose different ones. And basically what it's doing is it's got some measure on the y-axis of goodness of fit for the number of components. So it's your typical what we call a scree plot. You often see a thing called a scree plot, named after a scree slope. A scree slope, if you've ever been walking, is where you have a very steep cliff, and at the bottom where the rocks have collapsed down, it sort of has a build-up of boulders. So it has this cliff face, and then it sort of edges off. And when we get to PCA in detail, you'll see these things called a scree plot. Sometimes I call it an elbow plot as well, for obvious reasons. And often you're trying to choose. Sometimes that people will just go find the first point where it starts to level out. In this one, I actually looked and I decided eventually to choose 6. You notice that about 16, etc., you also probably have a slightly lower value, but I wanted a small number of predictors. So that's what I did. I went back to the data, ran PCR again, but this time I said the number of components I want is 6. I'm not doing any cross-validation or anything. I say, no, I've looked at my data. I think 6 is a good point. Then I went and get the coefficients, and what's really cool about PCR is it didn't return the coefficients in terms of the principal components. It's undone them and turned them in terms of the original predictors. Which is very nice. I had a bit of a smiley moment when that happened. I went, oh, that's so... Because before I'd never used PCR, I'd just done it by hand. And of course then I had these horrible principal components and I had to sort of faff around, and this does it automatically. Just remember that is on the scaled. So, that's really good, but as I said, Gary always goes, I'm surprised it works. So why should we be surprised it works? Because if you think about what we did before, is we took our predictors and we ignored the response variable. We just said, let's sort of transform this, taking into account the variability in the predictors. But it's a completely unsupervised method. When we did that transformation, we didn't care about the response. The fact that we somehow got it that there was a relationship between our response and the variability in the data was very nice, but it didn't have to be that way, did it? It doesn't have to be. You could have ended up, the first principal component could have been completely orthogonal, completely uncorrelated with your response variable. There was nothing that actually said, why don't we choose our first principal component to somehow be in line with the data itself, so the data response variable. So, to summarize, in PCR, the transformation of the predictors that we chose is completely unsupervised. You do this transformation purely on the predictors, and then you go and say, does this have a relationship with our response? Partial least squares gets around that. Partial least squares actually says, no, we're going to do a principal component analysis, but we're going to take into account the response variable. So you're going to sort of now start looking at the variability in the predictors that's also correlated with your response variable. So it's a supervised method. So let me run through how it actually does it. I'm not going to go into detail on this. I'm going to show you a paper that is really nice of explaining this. So I've got a little paper for you if you're interested in going further. So first of all, here's our procedure. We're going to standardize the P predictors. Then what you do is your first transformation, your Z1, what you do is, there's the general form. It's going to be Z1, you're going to get your phi's times your predictors. And we're going to set the phi's, we're going to take Y, and we're going to regress it on each predictor individually. So you're going to do P linear regressions. So you go and take your, in this case it would be salary, and you go and regress it on your CBRI or CRIB, and then you would get a slope. And you grab that slope, and that slope will be the value you would use. Then you go to the next predictor. So you're just doing simple linear regression. You say, how does your response and your predictor, how are they correlated? We will use that as our first coefficient. Fine, that makes sense. So how do we get to our next coefficients? You basically go back to your data and you adjust it. So you're going to adjust for that first one. So now you're going to take each variable again, each predictor, you're going to regress it on your Zi. So you look at the relationship between your Zi and your predictor. From that model, you get what's left over, the residuals from that model, and your residual becomes your new predictor. So let's recap that again. The first one, to get your coefficients, you just go along and you take each predictor one at a time with the response, you fit linear regression and use that relationship to get your coefficient. Then you say, now I've got that relationship, I want to get rid of it. I want to do almost a Gram-Schmidt. So I'm going to take off that relationship by getting the residual. So I get the residual by regressing each variable. So I go to the first predictor, I regress it on this new variable Z1, get the residuals from that linear model, and that becomes my new X1 predictor. Now I go back and I compute Z2 by taking the response and regress it on each of these new predictors, which is the residuals left over once I've taken away the Z1, and use that. Go through the whole process again and just keep doing it. So you're basically saying, I've taken into account this linear relationship, what's the noise that's left over, that becomes my new predictor, now I go and fit it again.
So to find Zm, you regress on Zm minus 1?
Yeah.
Okay.
We don't. We learn how to do the PLSR command. So again, built in. Looks very, very similar. Same package, salary tilde dot, data equals hitters, scale equals true, validation equals CV. Very, very similar. Really nice. And the way I like to think about it is this is BCR, where you're just saying, when I'm going to do my principal component analysis, take into account that response variable. You have that extra step that regresses it on that and does it backwards and forwards. We can do a validation plot. But I'm not going to go into detail with this because it's quite nice. And how you do principal component, I'll come back to this when we get to it. You don't do principal component. It's a standard thing, the mathematical theory and algorithm, how you do it. And then, of course, as soon as you did that, you'd either take forever and a day or it would break because computers don't work that way. So there's actually some very nice, clever algorithms to get principal components, etc. This paper I will put on Slack for you. In case you're asking why I don't put all the papers on the webpage, it's just a copyright issue. I can't put all these papers on a place that is freely accessible to the whole world without copyright. So I put them on Slack to you, but I don't put them on the webpage. This is quite an old paper now, it's 1986, but this has really, really nice visualizations of PCA, linear regression, multiple response, linear regression, partial least squares. The algorithms are a little bit tricky to go through. It's old style maths, but I do think it's one of the nicest explanations of it if you want to go into detail of this process. And that's it.
So with this one, do you take like 7 or 11?
Oh, let's have a look.
3.
Oh, that's a completely different graph to the one that's in the thing online.
Yeah,
Is it?
yeah. Because he has a different model, so yeah.
That's weird. It should be exactly the same. I just upload it automatically.
No, we're still getting the old one where you picked.
No, he's showing the partial least squares. He's not showing the.
Here's the old one.
Yeah, I'm just looking at the slides, but
Yeah, I mean, on this one, let's have a look. If we look at the adjusted cross validation, you've got 3, 4, 5, 3, 4, 4. I'd probably go to 3 components.
yeah.
If you want to do percentage variance explained, I might consider. I quite like 80%, so I might consider 6 components. I'm trying to see which is the lowest with the adjusted. The 3, 4, 4 seems to be the lowest. I can't find any lower than that. So I'd probably just go for 3 components in that one.
Yeah, which on that graph that looks right because that's where it starts to level out. That's
Yeah. Yeah.
Yeah, right. That's cool.
Any questions on that? So at this point, we've been doing lots of linear stuff. So next week, we're going to start non-linear. We're going to do splines and stuff. Cubic splines, natural splines, smoothing splines. You should try to write it, never mind having to listen to it. I've had 2 weeks of just reading about splines. You think they get boring after a while? You'd be so right. But hey, we can look forward to that. And then we do non-linear regression. Any questions? Cool. So see you next week. Remember, you have an assignment due. If you're having problems with the assignment, either come and see me, or if you want to know that I'll definitely be in my office 10 to 11 Fridays in my office. If you can't make that time, Slack me or email me and we'll try and make another time for you. Cool. Thank you very much. See you all Monday.
Yeah, I didn't try it.
Question 4 or 5 half. The detail we're doing, you RCCP